Is it good? We can go. Let's go to the first slide. This one. Yeah. Hello, everyone. I'm Arjun, and I'll be presenting about context-stated forecasting, progress so far, and next big challenges. This is joint work with a lot of collaborators. Took about a year for this work. Next slide. So this is just a safe harbor notice that the vehicle team if my company asked me to present. Just ignore it. When no promises to have any of this in products. That's what they want me to say. So this will be the agenda. First, motivation for the problem, why context matters in forecasting, and then the benchmark that we created to test this and to like start working on this direction, and then current methods and future directions. Some of you might have already seen this talk or read the paper. In which case, thank you for your patience in the next 30 minutes. So a brief about forecasting, you all probably know. It leverages statistical methods, judgment, or maybe both, predicts the evolution of key indicators, and then it's used to provide insights into critical business functions. Thank you. This is a problem setting just to establish the problem again. We focus on probabilistic forecasting here, where there's the time steps of history, and then there's P+1 to capital T future time steps that we want to predict. And given observations from potentially multiple time series, we want to estimate the joint distribution of their future values. Could be univariate, could be multivariate, but this is the problem setting that we call probabilistic forecasting here. All right, perfect. I got it. Okay, so this is the problem setting that is different from the one that I just presented. An observation is that in many forecasting use cases, you typically have a lot more information about the problem itself based on experience working on the problem or domain knowledge, more than just history and engineered covariates. So with experience, you can engineer more and more covariates, but there's typically this information that exists in your mind as a forecaster, or generally information that exists in the problem that you have. But typically models don't use that. Our goal is to build models that can be conditioned on any kinds of information that you know about the problem, essentially. So basically, the problem setting is modified to not just take into account history or engineered covariance, which is not here, or maybe is encompassed into context, in general context as a whole. So another observation is natural language is a very intuitive and universal interface to specify any kinds of additional information. This we know from years of research in language, etc., that the success of ChatGPT and all that is because language is a very easy interface to specify knowledge or to give information about something. So in this work, we assume that all context is available in natural language, but in the real world, I just want to preface by saying it might not be true. And there's at least two kinds of context that you can broadly think of. The first one could be background knowledge about the problem. So just the nature of the problem, the seasonality and all that. Maybe things that are derivatives of the history that are, additional information. Could be constraints about the problem. So in inventory optimization or all that, you have constraints. There's a maximum number of stock that you can store and all that. So these are constraints that you have about the problem that will significantly improve the forecast, of course, because it's going to make it more meaningful to you directly. Another kind of context is scenarios, which you would like to simulate. So in most cases, you just perform an unconditional forecast based on history and covariates, and that's your forecast. But then in many cases, you would like to condition it on certain scenarios or a certain set of scenarios, do a forecast for all those scenarios, and then take your decision, or then whichever forecast is appropriate according to the scenario that you expect to be true. These are broadly the two kinds of contexts we consider in this work. There is a link with judgmental forecasting here. Standard methods cannot consume the context that often unlocks the best forecasts. Again, this is linking to my previous slide, which sort of says that In many cases, your forecasts are limited by your forecasting models. Like if they can only consume covariates, then that's your forecast. A human has to modify it to judgmental corrections, or they have to merge it with their own forecast in many cases, which we see a lot in the literature. And in many cases, statistical and judgmental forecasts are independently generated and then combined. There's a huge literature on judgmental forecasting. Human judgmental forecasts and corrections are very, very useful. In most cases, necessary. But then they could be slow. They could be biased. They could be very expensive. Like if you have tens and thousands of forecasting problems, you need tens and thousands of humans if you really want to model each problem well, or you need a few humans who have expertise on broadly many of those. But in general, because humans modify the forecast manually, it could be very slow. It could also be very expensive because to maintain humans, you got to pay them. Also very unscalable. If you have millions of series, then with new domains, then if you don't have humans who have expertise in those domains, then your forecasts are not going to be ideal. Like they're not going to be the best forecast that you can get. They can also be biased and subjective, which we know. Let me stop coding. Oh, okay. Thanks. So our setup basically strives to achieve that, but by using models instead, using multimodal forecasting models. Could be LLMs. You can think of LLMs as an example of those. And the goal is to automatically improve a statistical forecast with all available information by using a model's judgment. It's definitely much faster, cheaper, and scalable compared to using humans. And it augments the forecasting pipeline, especially it did not replace the human in your forecasting pipeline, but it can augment them. It can make their job much, much faster if they can use a model to come up with the first judgmental correction and then modify it with their own judgmental corrections. It also allows for the use of large domain knowledge repositories. So databases from a company, you may have a lot of domain knowledge repositories in a company specific to a problem. If a human has to go through all of them and then assimilate them and then modify the forecast, it's going to be slow. Instead, you can use LLMs or big models to easily consume data. That's where I think they have an advantage in consuming a lot of data. And a note is LLMs also have biases. So all methods proposed in the literature of judgmental forecasting to overcome biases may still be applicable to this new area of research.
Just got a delay.
Sorry. I just want to preface again by saying our goal is not to change the space of forecasting here in general, not to make the next best forecasting models, but then target use cases where current forecasting models don't suffice. In the sense, humans often, use cases where humans modify these forecasts a lot, and these forecasts are subjective, etc. And then understand if context or additional information can help improve those forecasts, and then find a way to do this scalably, automatically with models. That's basically our goal and the scope.
Oh wait, otherwise mic gets back. Okay, I'll disconnect.
Okay. Next, going to the benchmark itself. So that's our problem setting, and how do we make progress in this direction? The first thing we did was build a benchmark that simulates how well models, that aims to simulate how well models fare at problems where context is necessary, not just optional. So it's a very new space. There was no data that when we started working on this problem, so we had to build a benchmark to measure progress and then to build models, etc. So the first thing we did was to build a benchmark. And the benchmark targets only those use cases where context is absolutely necessary. So there's this whole set of forecasting problems where context is not necessary at all. You could just get good performance with history, covariates, etc. We are not targeting that space here. We're targeting problems where time and again, you need additional information and humans have to come in and modify forecasts. These are problems where context is necessary. The benchmark is called context is key. It's a benchmark of forecasting tasks that require integrating context with historical data. So it's not just optional additional information. Every one of these tasks, the context is necessary to get the right forecast. And I'll tell you how. And we couldn't collect this context on a large scale, as we found that most context that we find on the internet is like very noisy, and they don't have a causal effect on the forecast itself. So we wrote each of these tasks ourselves. We wrote the context ourselves in many of these tasks, in all of these tasks, to make sure the context has a causal effect on your forecast, so that we can use it as a benchmark. It's definitely not scalable to write context ourselves, so this is just a first step in this direction. And again, accurate forecasts cannot be achieved without incorporating context. Next. Okay. An example task in the benchmark, that's your history right there. And next. So the ground truth is what you see in orange. And the best forecast that you can achieve with just the history is extrapolating this line here. That's your distribution. That is indeed the best forecast that you can achieve with just the history, because it's impossible to predict this drop. Now, with context, if you know that this is a series of power production of photovoltaic power plants in the state of Alabama, et cetera, you know that power production peaks at noon and then goes down as the sun sets. That's what you see. Next. If you give this context to a model, there are models which can understand this context and perform well. Now, we have 71 forecasting tasks just like this. Now, not exactly this kind of context. I'll come into that later. But tasks where, with the history, you would get a wrong forecast, wrong in the sense that it's completely different from what the actual ground truth is. With the context, there is 100% certainty that you would get the right forecasts, because the context causally influences most of the forecasting window, or at least part of the forecasting window. So our tasks have many diverse kinds of context. There's history, so information that is historical, that is not available from your numerical history itself. For example, if there were some spikes in the history, and if you just give it to any statistical model, it's going to replicate those spikes in the forecasting window, because it would think it's seasonality. But then if you give in the context that these spikes were anomalies, they were caused by this outage or whatever, that is going to give the model information that it doesn't have to replicate these spikes because they were anomalies, and it can focus on everything else. That is historical context about the history that is not available from just the numerical data. And then you have future context, which is scenarios, all kinds of scenarios that you want to simulate in the future in the prediction region. You have intemporal context. For example, the first sentence in this context is intemporal. It's just information about the problem that you know. That might be useful. That is just out there. That might be useful for forecasting. Then there's causal context. So if you have covariates, you can tell the model which covariate causally influences the variable, which covariates it's a correlation. So the model can use this information and not just model all the covariates the same way. And then you have covariates, of course. There's the next slide. There's one nuance to clarify here. How is this different from having covariates, which I've been asked again and again, which is a very good question. So covariates are just one kind of context, at least in our formulation, those that have been engineered to be useful for prediction. You know that these covariates are going to be useful. You find that they're useful because you know the process yourself, and then you're going to engineer them, and then you're going to use them in your forecasting process. If covariates solve your problem, then you should just use them. As a practitioner, this is one advice I can give. If covariates completely solve your problem, then you're best using covariates. But then covariates don't solve your problem. This might be of interest. We are targeting problems where we want to condition on free-form text and don't want to engineer covariates, or there are too many covariates to be modeled and we would like to just dump all site information in the model if the site information is available in a flexible format. Or new events keep happening again and again, and every time a new event happens, you need to add a new covariate for the event. In this case, having everything in a free-form text puts things in a unified space. You don't even have to model every covariate if you assume that your context covers everything. Those are the kind of problems we're targeting. So coming back to the kinds of context in our benchmark, those are the 5 kinds of context. Next. So another challenge that we came up with when making this benchmark was, how do we ensure that the text we write is diverse in terms of what the text has? So the text could first of all, directly have information about the future. It could just say the value tomorrow is going to be 30. Now that's going to be useless. Yeah, you're never going to have that sort of information in the real world. But we could have just done that for the sake of the benchmark, but we didn't want to do that. We had to find a way to make sure that there's, for example, in some tasks, there's a lot of information in the context, use of a prediction, but then in some tasks, there's information, but the model has to do some deduction, or it has to make some analogies to succeed at the forecasting tasks. So from literature in language models, you know that capabilities exist. There's a huge literature on what capabilities language models have, etc. And since we have some expertise in LLMs, we use that to label each task with capabilities that a model may require to solve the problem. For example, in this case, you have some intemporal information there. It has to deduce that from the power production, from the line that this series contains the power production, there has to be a deduction step that infers that, okay, this is power production, which means at noon, it's going to be, it's going to go down from you. So one choice is giving this information in the benchmark. We could just say from noon, it's going to go down. But then if you want the model to deduce, if you want to encourage the use of capabilities, we just say this is power production. The model is expected to deduce and then use information. There's other capabilities. There's a huge literature in judgmental forecasting, which I love, which is making analogies. We also have some tasks which require analogical reasoning, where the context has different series, different contexts. The model has to make the analogy to the most similar series and then use that as a context to be used. Other capabilities that I don't want to go into because of time, but you can find in the paper. Next. The next slide. Also, we made sure the benchmark is diverse in terms of domains. There's all these domains in the benchmark. And again, the definition of the domain is pretty loose. We just label each task with a domain, but then these might not be exactly concretely different domains. It's just to give an idea of where the benchmark stands. Next. So that's our benchmark. We now have a test bed. What's the next step? We benchmark models. Next slide. So coming to current approaches and future directions. These are existing forecasting methods. You have traditional models that are simple, fast, they work really well. You fit them to historical data, or you can add covariates. Then you have foundation models that are pre-trained on large amounts of time series. They can also do good forecasting. These two set of models cannot handle any context in natural language, as you know. And then the only kind of models that can handle natural language right now are obviously language models. You would just prompt an LLM. That's one of the methods you can use. And these are models that are not trained for forecasting at all, as you know. They're trained for doing natural language processing. But they're the only models that can use both, that you can give a time series and a free-form text both in the prompt. So we benchmarked them. This is the prompt that we used in our paper. We just say, I have a time series forecasting task for you. Here's some context about the task. Make sure to factor in any background knowledge, etc. We put the context where the context is, and then we give the history. We say predict the value at the future time steps, return the forecast, and that's the expected output. The next slide. An example, this is how you exactly put the prompt. And LLMs are pretty flexible, I would say. You can give irregular time series, they're not going to care. You can put loads of context within those tags, and they're going to consume all information. So they're pretty flexible in this aspect. And you can also constrain the output format to be exactly the format you want. So you don't have to have any uncertainty about, oh, okay, so will the output format follow the format that I set? There are tools with which you can constrain the output format to be this length, and with this only numbers at this point, or only decimal points and all that. So we use those tools. And yeah, so coming to probabilistic forecasting, CRPS is a well-known metric. But when there are some regions in the prediction window where the context is required, then if you just take an average CRPS over your prediction window, those windows could just be hidden in the average. There would be no difference between a model that does not use the context versus a model that uses the context, because the context only affects a few time steps. You could just be averaged out. For example, in this task, The context says that in 3 hours, a heat wave struck the city and began on 9th of October and lasted approximately for 3 hours. And power consumption was 5 times the typical usage. And as you can see from here, consumption is 5 times the actual value. If you just take the CRPS, average CRPS over this, then it's very easy to ignore this spike. In many cases, it may not be this high, but it could just be this high, in which your CRPS could just ignore it. So we developed a metric that's an adaptation of CRPS called the Region-of-Interest CRPS. So we marked regions of interest in every task, where these are prediction timestamps where context is changing the forecast. Outside these regions, you don't need context at all. But in these regions, you absolutely need the context to perform well. And our CRPS, or region of interest CRPS, is defined as half the CRPS within just this region, half outside, and then also a formulation which we had to measure constraint violations. So if you have any constraints such that this electricity usage will never go beyond 16,000, you can put that constraint and your metric is going to measure violations. These are the results of models. We benchmarked statistical models, some foundation models, and language models. So some broad observations. We were surprised by how language models could do this task pretty well. The task that I mean is take a context and then apply it on a forecast. It's not forecasting, it's just forecast modification. You could think of it as modifying a forecast based on context. Also, statistical models and foundation models are expected to fail in our benchmark because we built a benchmark technique. These are tasks where you need the context. So any model that does not use the context will definitely fail. And another observation is the biggest language models do the best. There's a 400 billion parameter model that achieves the best performance in the benchmark. Smaller models don't do as well. Yeah, that's pretty much it. The next slide. Some example forecasts to show how these models do forecasting. Without the context, that's the best forecast that you can get. With the context that this is the number of field fire incidents, you can see that in the winter, these incidents go down. So Llama 405B can use this context and get a much more accurate forecast. Another example, which we took from the PEMS traffic data set. The context here is that 4th of July is a holiday in the US. So traffic typically reduces in that freeway. So without the context, the forecast is just an extrapolation of the history, which is a great forecast, which is a good forecast if you don't have any context. With the context, it could use this forecast and then calculate an appropriate drop and also have a pretty decent uncertainty interval. Next slide. Another task where there's a constraint. The context here is that the inventory is limited and the values are bounded above by that number. Models can easily apply that constraint. This is a pretty easy task. There's a demo that I wanted to present, but then I don't think they'll work here. Okay, so areas of improvement. That was just the results that we got from language models, but then it's a very new benchmark. Language models are the only thing you can benchmark in this space, so you're expected to see some results, but then there are a lot of directions of improvement and healthy skepticism that is encouraged here. In some tasks, GPT-4 and other models, when you don't give the context, they can do forecasting pretty well. When you do give the context, they go crazy with the forecasts. Forecasts are at 2000 and all that, while the ground truth is at 40. Maybe they misunderstood the context, but we have no idea how this happened. A forecast going from 40 to 2000, they're off by 5,000%, but just when giving the context, which means it's having some domain knowledge about this context, which is completely wrong or completely misspecified. Next. Also coming to inference times, they are slower by 1 to 2 orders of magnitude, which is impractical by any means to be used in real-world applications. On this side, you have ETS, ARIMA, and maybe even Chronos, TimeGen, Moirai, and all that, which are extremely efficient. And then you have LLMs, on the other hand. As the size grows, as it goes from 8 billion parameters to 405 billion parameters, inference time just increases by orders of magnitude. So although good as a research direction, these are not going to be deployed in any means unless they become more efficient, which I'll touch on later. Next slide. Also, yeah, that's another way to look at this. You have parameter count and you have aggregate CRPS on the benchmark, or CRPS on the benchmark. If you look at statistical models, they are extremely parameter efficient because they have very few parameters, but then they don't perform well on the benchmark because this is not a benchmark meant for them. Then you have the best performing language models. They are great at the benchmark, but then their parameter count is just way off. Now we want to go in the direction where this is the Pareto front, by the way, and you want to improve on the Pareto front. You want to make models efficient while preserving their performance on the benchmark. That's a way to make progress here. Next slide. And there has been a lot of progress in this space, more data sets apart from ours. One even from Christoph's group, I suppose. So this is a very active space of research if you want to work on it. Important future directions that I want to highlight. One being real-world data sets. So what we built was a very synthetic way of looking at the problem. We wrote the context ourselves based on our goal, which was to have a benchmark where you need the context, but then in the real world, this could be completely different. You could have different kinds of context. You could have different amounts of context. So we need more real-world data sets to do research in this space. It can be use case specific, potentially one that has data from interaction with users and how they modify forecasts to judgmental corrections, etc. They probably already exist and companies are using them, but then I don't think they're released, obvious reasons. But even if I think we should find a way to do research in this space without having to ask companies for their data. I think it's possible. The next direction is efficient models. We want to build more efficient models, as I highlighted, and do cost-benefit analyses of these models because they're very new. You want to see if the cost is worth taking for the benefit that they will give in applications. Also, building models that are good at normal forecasting tasks. If you use LLMs at forecasting, you know they're really bad at normal forecasting tasks. But then when you come to context data forecasting tasks, they're the only models that can consume text. But you don't want a separate model for context data forecasting and a separate model for forecasting. You ideally want one that can do both. So building models that are good at both generic forecasting and context data forecasting, and maybe even agentic interfaces, as Azul touched earlier, models that can use databases automatically through tool calling, which is a very new concept in agents, where the model can use tools to interact with databases and automatically retrieve information without the human having to put information in the prompt themselves. It's just reducing one layer of complexity, but that's also an interesting direction to pursue. That's it. There's a website where you can visualize all tasks in the benchmark. There's 71 tasks in total, for which we wrote context. And then the benchmark, models, experimentation code, everything to reproduce the paper is on GitHub. You can look at it. Even the prompts that we used for these LLMs. And the paper is also available. A lot more examples in the paper, a lot more results, a lot more criticism on these models that you can look into for the paper. That's it. Thank you.
Thank you.
Yes, mate.
Thank you.
Should I get closer to the microphone? Or?
No, like,
Okay. Thank you very much. I liked it a lot. I have to say that I was missing talking about the covariates and the context, because at least from the very applied approach, thinking about real challenges in forecasting without considering covariates, it's really naive, because I understand not to use it before, but reality is it, context is key. Maybe there are many questions. At least I will start with one that it's a little bit picky, but I think in the examples that you show, maybe just bad luck, or but the thing that would be happening is you are just encoding the covariate in text. For example, just telling what is going to be temperature, or if it's going to be vacations or not, or holiday. It's something that we have been doing for many time, just like one dummy variable as a covariate. Yeah. So just wondering if, just to understand better, you could give us some examples where it's not exactly something that you could encode as a covariate.
Yeah. There's a lot of the example that I presented with holiday was just an example with covariates, but there's a lot of tasks in our benchmark where you cannot encode it as covariance. For example, I will have to look at the tasks in the benchmark. There's a website for it. If you just
We can do, yeah, but then like I was like concerning about that possibility. Yeah, maybe in that way, if you think that this could help a lot to actually analyzing some context to the LLMs, checking what they are extracting actually, and give tips about what covariates you really need to start recording or retrieving from your historical data and inject in your forecasting models.
Yeah, that's a very good future direction to give to use it for selecting covariates. So the covariates that we had in our task was just to make tasks where to test if models can use covariates in natural language, because potentially a user might just dump those information in language. But coming from an applied point of view as a practitioner, you should be using covariates for those problems. So we're targeting problems where you cannot use covariates, and there are some examples in the benchmark that I will show you later where maybe it's difficult to make a covariate, or you wouldn't have seen that coming, and you would have to make a covariate after you see the first instance, but you have some information in text that you can, if you put it there, the model is just going to understand. So there are tasks like that as well, benchmark.
Something like a pandemic is coming, or it seems that there is a new medical issue in a close country. Yeah, maybe it's impossible to see attack the variance in your historical data. That is
Yeah, a more balanced take would be use covariates and backtest how it happens. Use context and see backtest how it performs. If context works better, use that as a practitioner. The benchmark was just though to make progress in the space of understanding natural language.
And I also want to add that it's super interesting what you mentioned about the capability that is offered to make simulations. If you go to the stakeholders, they will have like 100 scenarios in mind, and to make a good decision, maybe they don't need all of them, but probably they want to try all of them. So as you see us changing with text, the scenario formation context that this may happen and seeing the impact would be amazing. More question, maybe one question.
Yeah, so super interesting. I disagree with the model selection, but that's another story. My question is on model, like it's very difficult to scale, like as we said later. Like my question is, how much of context writing can we automate? Like from your experience writing content, like all these prompts, how much of this can be automated? Like for example, I have 5,000 retail cancers daily, 5 years. I cannot write it manually. So if I could automate it somehow, access internet, denoise, like, do you think that this is feasible, or we should always annotate manually? Like,
So
you can do with covariates.
yeah,
Yeah.
So follow-up work just that we're currently working on is basically having a gold standard set of context that you wrote manually, say 10 examples or 12 examples, giving it to a language model, asking it to write the context. And then an important step after this is using a different language model to verify that these contexts are useful. If not, do this process all over again. It's called LLM as the judge. There's literature on that, which you can use.
Yeah. But on the side of automation, have you used this, your approach you're discussing, right? Written 10 examples and then have it, the Gen framework to actually scale it up? You have some work there?
No, we're still working on it right now. We're trying to build a more scalable benchmark that is basically an extension of this.
Nice.
And we found that this concept of using an LLM to write the context.
Yeah, that's fun.
So initially, we just used the LLM and we expected that the context would be useful, but then it turns out LLMs can make mistakes a lot. So it required about 5 iterations back and forth between 2 LLMs to talk to each other, and then you can get more meaningful context.
Sounds a lot like reasoning in LLMs.
Yeah, exactly.
So you are working on that. We can expect some.
Yeah, super. Yeah.
And
Go on.
how?
Why not?
Say I want to use another model. Model trained specific on my domain, that my domain either it's embeddings or covariates in either format.
Yeah.
Can I take the context and somehow automatically convert it into of covariates? Like, do you think that is feasible? Like, combine?
Yeah, it works for your domain. If you can convert them to covariates, you would lose some information. But if you can train a model that can convert context to covariates, and if it works, you should use that, because covariates are much easy to understand. There's a finite set of covariates. But maybe if that does not give you the performance that you really want in your application, exploring context with an LLM field. Yeah, there's one idea that we're working on again, where you have a model that you've built with years of expertise. We don't want to change the model for a context data forecasting model. Use an LLM to convert the context to a representation or an embedding. You just train an adapter between these two that will maintain the performance of your forecasting model. But then when you have context, you have this additional model that you can basically add, or you can change the forecast. Basically, every point of the forecast, you do plus or minus, and then it will maintain performance on your tasks. But when you have the context, you can augment it.
Yes,
It's the ongoing work I can discuss.
thanks for that. Yeah.
Very cool idea. Well, I think it's clear to everyone that context will be key in the future. So please join me again in thanking Ashok.